Okay, a 20 centimeter long metal rod CD is moved at speed of 25 meter per second across a uniform magnetic field of flux density 250 millitesla. The motion of the rod is perpendicular to the magnetic field as shown in figure below. Okay, calculate the motional induced EMF in the rod. First of all, we first look at the question A. Yeah, we first do the question A. So all right. So here these questions. Hold on a second. All right. So here we want to find the motional induced EMF in the rod. Okay. So this is considered the straight conductor. Okay. EMF induced in straight conductor. Okay. Moving along a magnetic field. So we want to find the induced EMF. Okay. The rod is a straight conductor. So we already have the length. The length of the rod is the length. We have the length of the rod in centimeter. We need to change to meter. We have the speed also. Uniform magnetic field or flux density. Okay, the word flux density is magnetic field strength. Yeah, it's the same. The flux density is the same as field strength. Okay. You also can check the unit is Tesla. Tesla is a unit for magnetic field strength. Okay, it's the unit for B. Tesla. Yeah, flux density. So field strength has another name, flux density. Okay, so that's the value of magnetic field strength. Now the motion of rod is perpendicular to the magnetic field. So the motion means the velocity is perpendicular to magnetic field. So what he means here is he said velocity is perpendicular to magnetic field. So why is this important? Later you will know. Okay, and do the question A. Yeah, let us first do the question A. So to find the induced EMF in the rod, actually it's very simple. It's just use the formula, LV cross B. LV cross B. So that's the induced EMF in straight conductor. Let me find, where is it? Okay. Induced EMF in straight conductor. Yeah, induced EMF in straight conductor. So is LV cross B. So the formula is BLV sin theta. Yeah. So it's BLV sin theta. And then the theta is the angle between this V and B. Angle between this velocity and magnetic field. Yeah, that's the angle theta. And that's why he here the question he said the motion of the rod is perpendicular to magnetic field. The velocity is perpendicular to magnetic field. So this clearly shows that the theta between V and B is 90 degree. It's 90 degree. This theta is actually between the V cross B. Yeah, angle between these two. So since he say V is perpendicular to B, so this theta is 90. This theta is 90 degree. So we can put it BLV sine 90. Okay, and then we know that sine 90 is equal to 1. Sine 90 is equal to 1. Okay, maximum. So so we can calculate. So the magnetic field, what's the magnetic field strength is the 250 millitesla, which is 0.25 Tesla. Okay, 0.25 Tesla, and length is 20 centimeter, which is 0.02 meter. Okay. Yeah, no. Centimeter change to meter is divided by 100. Understand? 20 centimeter change to meter is divided by 100, not divided by 1000. Divided by 100, so it's 0.2 only. 0.2, not 0.02. Okay. Velocity is 25. 25, and then sine 90 is 1. Okay, so what's the answer? Let's calculate first. Calculate 0.25. multiply 0.2, multiply 25. So I got 1.25 volt. Okay, 1.25 volt, that's the answer. Am I right? Okay, so the answer is correct, 1.25 volt. That's correct. Good. So I got my induced EMF already. Now look at the second question. Okay, B. If the rod is connected in series with resistor of resistance 15 ohm, okay, determine the induced current and its direction. Okay, let's do question 1 first. So now he said that the rod is in series with resistor of resistance. This is the resistance. Okay. So find the induced current. Okay, find the induced current and the direction. Okay, find the direction also. So remember, when this rod is moving, it already become a battery. It become like a battery. Because you have induced EMF in the rod. So now you connect the rod with a resistor. This rod will become a battery already. So it become something become like this one. Yeah, maybe hold on a second. Yeah. Okay. So now here you can see I have drawn out. Okay. So you can see now the conductor is connected in series with a resistor. Okay, connected in series with a resistor. Okay, so this CD is moving to the right. Now, when this rod CD move to the right, move to the left. Okay, move to the left. So it become like a battery. It become like a battery because it got induced EMF. Because we know that the battery give out EMF, isn't it? So this one, yeah, induced EMF means it become become a battery, like a cell, yeah. So we can say that this thing has become something like how to say okay, let me draw out. Maybe it becomes this has become a circuit like something like this resistor. Okay, I'm not sure what direction of this battery yet because I haven't checked the direction of the induced current. Okay, maybe it becomes like induced current, like induced EMF like this. Okay, because this CD has become like a battery. Yeah, has become like a battery because got induced EMF, so that means it become like a battery. So it got, it got current, induced current, got positive, got negative. Okay, got induced current. So in the circuit now it has current. Understand? It got induced current. When you have induced EMF, you must have induced current. You must have induced current. When you have induced EMF, you must have induced current. Okay, so this the direction of the battery, I'm not sure yet because I haven't checked the direction of the current. So this direction of the battery may be wrong. Yeah, may be wrong. Later I will teach you how to find the direction of the induced EMF, or also how to find the direction of the induced current. Okay, so right now we just want to find the magnitude of induced current first. Okay, magnitude of the induced current first. So we already got the induced EMF. So how to find the induced current? Very simple. Induced, yeah, just use the Ohm's law. Induced EMF equal to induced current times resistance. This is just like you can say is Ohm's law. Ohm's law. Yeah, E equal to IR. Okay, so induced EMF is 1.25 volt. Then induced current times resistance. Resistance is 15 ohm. Okay, in 15 ohm. Okay, so 1.25, so divide by 15 ohm. Okay, I get 0.083 ampere. So that's the induced current. Am I right? Yes, that's correct. Yeah, 8.33 exponent negative 2 ampere is the same as this one lah. Okay, So just use E equal to IR, Ohm's law, and you can do it. Yeah. Now I want to find direction. Yeah, I want to find direction of this induced current. So is this current clockwise? Yeah, is the current produced by this rod CD produce a clockwise current? Clockwise induced current. So this one you have to. There are two methods. I will teach you two methods to get this direction of induced EMF and direction of induced current. Okay. So first of all, I want to list out. Yeah. Okay. This one later on I will show you another thing. Okay. So I will show you two methods. Yeah. I will show you two methods. Okay. So there are two for direction of induced EMF or induced current for straight conductor. Oh, sorry. For straight conductor. Okay. There are two methods. Okay. So first of all, let's talk. Okay. What are the two methods? What are the two methods? So this is the first method, and and second method. Okay. Okay. First method is using right hand rule. Right hand rule. Okay, right hand rule, which I have teach in my lecture video, my classroom teaching video. I've thought about this right hand rule. Okay, so right hand rule means I use the thumb and then this finger, forefinger. Okay, you know. Okay, let me see. Yeah, it's because it's like cross product, right? It's like cross product between V and B. Yeah, induced EMF is like, you know, the induced EMF is just like this one. You see that? It's V cross B. It's V cross B. So the finger, the forefinger shows the velocity is V first. V, the forefinger is the V, and then the palm. This is the palm. It shows the direction of magnetic field. Understand? Because it's V cross B. V cross B. So it's forefinger is V. And then the magnetic field is the palm. Yeah, it's like V cross B. Understand? It's like V cross B. V goes to B. V cross B. What is this? Okay, and then finally is the induced EMF. Induced EMF is the thumb. The thumb is the induced EMF, or you can say this is the direction of induced current. Why we can say this is also direction of induced current? Because let me write out the formula again. This is between LV cross B, isn't it? LV cross B. So E induced is equal to IR. E equal to IR. So E induced is actually also I induced R. I induced R. LV cross B. So that's why the direction of induced EMF is also the direction of induced current. So when the thumb shows the direction of induced EMF, the thumb also actually shows the direction of induced current. Understand? When the thumb shows the direction of induced EMF, it also shows the direction of induced current. Okay. So this is the V is the forefinger. I just want to write it. This one is the forefinger. This one is the palm. Yeah, forefinger cross to palm. Finally, this one is the thumb. Understand? This one is the thumb. So maybe I should put it over here. This is the first method. Okay. So this I want to show you. How I get the direction of induced EMF or induced current using this first method, right hand rule. Okay. So remember, this is your right hand, right hand, not left hand. It's a right hand, So the forefinger is the velocity, the palm is the magnetic field, the thumb is the induced EMF or induced current. Okay, now I'm going to show you. Okay, I'm going to show you. Okay, so here I already drawn out. Okay, I have drawn out the diagram for you and to see. Okay, so you can see this this rod CD is moving to the left, isn't it? It's moving to the left. Am I right? Okay. Yeah, it's moving to the left. Yeah. So I use my right hand rule. Yeah. I use my right hand rule. This one. Okay. I want this one. I use my right hand rule. Forefinger is the velocity. The palm is the magnetic field, and then the thumb is the induced EMF or induced current. Okay. So now I'm going to show you. Okay. Again, the forefinger is the velocity, and then the palm is the magnetic field, and then the thumb is the induced EMF or induced current. Okay, so velocity goes to the left, magnetic field go out of the paper. So you see, forefinger is the velocity, goes this side. And then the palm is the magnetic field. The palm is the magnetic field. Okay, velocity goes to the left, magnetic field go out of the paper. See, so my palm should point. My palm should point out of the paper. My palm should point out of the paper. So why is my thumb? My thumb is going up. My thumb is going up. See that? My thumb is going up. Can you see that? So my velocity goes to the left, my palm goes out of the paper because the magnetic field go out of paper. So my palm should go out of the paper. So my thumb is going up. My thumb is the induced EMF or induced current. So my thumb is going up. So the EMF direction is from D to C, because my thumb is going up. Or the induced current should go from D to C. You see, where's my direction of thumb? My thumb is upward. So it's the induced EMF is from D to C. So how should I draw? So the induced EMF is this one should be positive, this one should be negative. So my EMF direction is this side. This is my induced EMF direction. Understand? This is my induced EMF direction, and this one should be positive, this one should be negative. Okay, because you see, velocity goes there, magnetic field go out, so my thumb is going up, so my induced EMF is upward. So my current also go upward. My induced current also go upward. So my induced current is going this side. So my induced current is clockwise. Can you see that? So my induced, you see my induced EMF is going up. So my induced EMF is going up means the positive terminal is at the top, the negative terminal is at the bottom. So induced current is also going up, and then here it go out, and then go down, and go to the left, and then go up. Induced current go up. Yeah, so it's clockwise. So for resistor part, induced current is actually going down. Understand? So in the direction of induced current is clockwise. Okay. So all right. So let's go back. Yeah. Okay. So let me draw it over here. Okay. I want to draw it over here, this one. All right. Okay, so just now using this right hand rule method, I found out that my induced current actually is going up. My induced EMF is actually going up. Okay, so same goes to my induced current direction also, in the same direction, going up. So induced current come out from here, and then go down from here, and then goes to here. Okay. So my induced EMF direction, using this right hand rule method, I found my induced EMF is going up. So same goes to my induced current, also going up. So induced current go up. So the induced current come out from C, goes to the resistor, goes to the D, and then enters D. So and then goes up again. Yeah, repeat the cycle. So I can say that the NC here is actually the positive terminal. Is the positive terminal because the current come out from the positive terminal, and then current enter the negative terminal. I enter the negative terminal. Okay, so this one is the positive terminal. This one is the negative terminal. So it becomes what? It becomes something like maybe I draw below here. So it becomes like something like this one. Understand? So the NC is a positive terminal, so that's why this one is a positive terminal, this one is a negative terminal, and the induced current come out, go, so this is the induced current direction. Yeah, like this is the D, this is the oops, this is the D, this is the C. Yeah, I can say. Okay. So induced EMF direction is this one. This is the induced EMF direction. Induced EMF direction is always from negative to positive terminal. Okay. So what is the direction of the induced current? Direction of induced current is I can say is from C. Direction is from what is the direction of induced current? So direction of induced current is from D to C. D to C. That's the answer. From D to C, or upwards. Yeah, upwards. Yeah. For rod is upwards. If rod, it is upwards. But if for the resistor, it's downward. So it's different thing. For rod, is upwards from D to C. But for resistor, it's downward. So you need to check the question. Is say the direction of current in the resistor, or is it direction of current in the rod DC? If in the rod DC, the direction of current is upward. But in the resistor, the direction of current is downward. Okay. That's the first method. Using the right hand rule, very simple. Okay, so okay, wait a second. Okay, now I want to teach you the second method of finding this direction of induced EMF or induced current. Okay, and the second method is find the change of flux in terms of area. Change of flux in terms of area. Or we can say in terms of change of area. Okay, and then we use right hand grip rule. We use right hand grip rule. To find out the direction of induced current. Okay, the right hand grip rule is the one you have learned. It's not the right hand rule. It's the right hand grip rule. This one very simple. Right hand grip rule means like this. Okay, right hand grip rule means just okay, this okay, let me see. Okay, the thumb is the induced magnetic field, or induced flux. Okay, the thumb is the induced magnetic field or induced flux, and then the finger is the induced current. Understand? The finger is the induced. The forefinger is the which we grip. Yes, it's a right hand grip rule. The forefinger is the induced current, and the thumb is the induced magnetic field or induced flux. Okay. So now let's check. I want you to first look at what happened. Okay, I want to draw this picture first. Let me draw it over here. Okay, I want you to check this one. Okay, so I want to ask you, yeah, that this is the second method. You see, notice what happened to the change of flux and the change of area first. Okay, and then apply Lenz's law, and then apply Lenz's law. Okay, and also plus Lenz's law lah. Okay, plus Lenz's law. Okay, look at here. When CD goes to the left, what happened? When CD, okay, this is the original area, right? Original area, yeah. For this question, CD, I just draw a resistor, yeah. I just draw a resistor, and this is a CD. Okay, originally, yeah. Let's first look at the original area. Okay, original area is this. This is the original area, right? Original area. Okay, original area. This amount of area is the amount of magnetic flux. Because the black one is the magnetic field, yeah, original magnetic field. So this area has the magnetic flux. Understand? Magnetic flux. Now, if CD goes to the left, when CD goes to the left, maybe goes to here, CD. So what happened to the area? Is it become bigger or become smaller? Is it become bigger or become smaller? It becomes bigger. Now it has more area. Yeah. How to draw? Yeah. So it becomes bigger already. See that? More area, isn't it? So what I can say is, okay, first thing, what is the change of flux? Yeah, what is the change of, okay, what's the first thing you say about change of flux? What's the first thing you can say about change of flux? Okay, flux increases because area increase, isn't it? Flux increase because area increase. Yeah, when CD goes to the left, so flux increase because area increase. Yeah, you see, because it's from I can say from you know, yellow become green. Yeah, yellow become green. So the first original is the yellow area, but when CD goes to the left, the area has become more. Yeah, so the flux become more. Okay, so this is the change of flux. There is a change of flux, isn't it? So what happened is what the Lenz's law says. So the Lenz's law says that to oppose the change. Oppose a change. We must oppose a change. So how to oppose the change? The key is oppose the change. So the change is flux increase, isn't it? Area increase. Yeah, flux increase because area increase. So to oppose a change, I want to decrease back the flux. So according to the notes, yeah, referring back to the notes, if you still remember, you see the flux increase. The flux increase. So Lenz's law to say to oppose the increase of flux, I must produce opposite flux. I must produce opposite flux. Understand? Okay. So to oppose the change, when flux increase, I want to decrease back the flux. Understand? I want to decrease back the flux. So I want to decrease back the flux. So how to decrease back the flux? I must to oppose means to you know, go against the, when something increase, Lenz's law try to reduce the increase. Reduce the increase by decreasing the flux. Okay, when flux increase, I want to decrease. When flux decrease, I want to increase. That is what I mean, oppose the change. Yeah, I want to decrease the flux. So how to decrease the flux? I must produce. So the coil produce opposite flux. Produce opposite flux. Okay, or opposite induced magnetic field. Produce opposite magnetic field. So because the flux has increased, you see the yellow area become the green area, the flux has definitely increased. So to oppose the increase, I want to decrease the flux, so that this coil will produce opposite direction flux. How to produce opposite direction flux? That means the original flux is going out of paper. This coil will produce flux that go into the paper. So it will produce magnetic field that go into paper. Excuse me. So this is the induced magnetic field by who? This is produced by the coil. Coil produce this magnetic field. This induced magnetic field actually comes from the coil. Understand? Come from the coil. Okay. So it got induced magnetic field into the paper. So now now I already got the direction of induced magnetic field. So now I'm going to use right hand grid rule to find the induced current in this coil. Okay, so let's look in my camera. Okay, I will show you my camera. Remember, the finger is the induced current and the thumb is the magnetic field. Okay, the thumb is the magnetic field. Remember this one. Okay, let's check. Okay, I've drawn this one. Okay, like this one. You see that? So so this coil has produced induced magnetic field into the paper, isn't it? Induced magnetic field into the paper. So I use my right hand grid rule. The finger is the induced current. The finger is the induced current, and the thumb is the magnetic field. The thumb is the magnetic field. So the thumb is the induced magnetic field. The finger is the induced current. So my induced magnetic field is go into paper. So my induced current is clockwise. My induced current is clockwise. So my induced current is clockwise in the coil. Okay, so my induced current is clockwise. Understand? See that? Remember, this right hand grid rule is just for the induced magnetic field. Induced magnetic field. The thumb shows the induced magnetic field, not the original magnetic field. Not the one going out from the paper, but the one induced. Okay, the one induced. So induced magnetic field is going into paper. So my finger is the induced current. So my induced current is clockwise. Okay, going back to my slide. All right. Let's check. Okay, so look at this one. So I found out my induced current after I use my right hand grid rule. I found out my induced current is clockwise. So my induced current, that's my induced current. So is it the same direction as I have predicted in the first method? Is it the same direction? Clockwise also? Yes. The first method found out the induced current is clockwise. The second method also found out my induced current is clockwise. So both method is acceptable. Either you use this one, the velocity magnetic field induced EMF, or you use find the change of flux through the change of area. Right hand grid rule to find the induced current. You also can find the same direction of induced current, which is clockwise. Okay, so I think this is the first part of my video. The next part I will explain in more detail, for more using another example. Okay, That's all. Please go to my second video. Okay, thank you.